Welcome, students, to this continued series on machines. So, last time I have given you a question that what is, if suppose you have an ideal machine and it is given that the ratio of displacement, so ratio of the load is to effort is given by this ratio. Okay, and now you have to tell me that what is the mechanical advantage and what is the load if effort applied is 14 Newton, is it? So I hope you would have done it, and I could not see any comments so far. And but if someone has any problem, we will discuss it this time. Now, uh, by this equation shown here, I know this mechanical advantage is equal to velocity ratio into efficiency. And when we say that it is an ideal machine, okay, so ideal machine itself tell you that the efficiency is 100%, correct? Now, what you have to do is convert this efficiency percentage into a fraction. How do you do that? And one of the important thing. So I have given you the ratio of load by effort. So what is load by effort? So load by effort is nothing but 1 by velocity ratio, isn't it? So your velocity ratio is basically the ratio of load by effort. Okay. Okay. Sorry, I have written something wrong there. Uh, yes. So you know uh, your velocity ratio is basically effort by load. So I was saying it right, and okay. So this is what we are given. Okay. So velocity ratio is the ratio of effort by load. That means 1 upon velocity ratio is dl by de. Okay. Now you can put this here. So if I get v velocity ratio, it would be 3, isn't it? So 1 by 3 is equal to 1 by velocity ratio is simply giving you velocity ratio equal to 3. And if I put the value 3 into, so mechanical, so your efficiency is 100%. So 100% is converted into fraction. So 100 is 100, that is 1, and the value is 3. So it shows that when we have ideal machine, we have learned it earlier that uh, this velocity ratio is equal to mechanical advantage, and that's what we have obtained here numerically. Now, let's go to the other part where you have given that your effort is, you know, effort is given that is 40 Newton, and mechanical advantage you have already obtained is equal to 3. Then what will be your load? So mechanical advantage is the ratio of load by effort. So I will write it. Mechanical advantage is load by effort. So if you put the value of effort and mechanical advantage, so load is coming out to be 120 Newton straight away. Okay. So this is how you will do questions based on this formula. So you should remember it because you know let someone ask you in multiple choice question. So if you know this formula, you will give your answers within 2 seconds. So if he says that consider it as an ideal machine, you know that mechanical advantage is equal to your velocity ratio. Okay. And let's come to the second question that I have asked. So the question was that how mechanical advantage is increased given the situation we have on figure. So in order to increase, so first let us see what is the formula for mechanical advantage for levers. Okay, mechanical advantage for levers. So last time we have learned that it is the ratio of effort arm by load arm, isn't it? And if you know that it is the ratio of effort by load, then how you can increase the value of MA? So the answer is straightforward. Either you decrease, sorry, either you decrease load arm, that you make a load arm shorter, or you can increase your effort arm, that will also make a same thing. So effort arm longer. So these are the two ways by which you can increase your mechanical advantages in levers. So if you make in a lever your effort arm is big, you will have to give input less force, and you will obtain a large force out of it. Okay, and let's now go to the another topic. Okay, so this is basically classification of levers. So in classification of levers, you will study that how levers in different situations can be used as force multiplier, speed gainer, or simply as a measuring balance. So physical balances, you would have often seen this on the shopkeepers, where they have this physical balance, and it is having two, pockets where you put things on one and weights on other. So you will know what is the weights of that particular thing. So classification of lever is based on where the fulcrum is placed. Okay, and depending on that, it can be divided into three classes: class 1, class 2, and class 3. So basic difference is that in class 1 your fulcrum is in between effort and load arm. So effort and load point. Okay, so if I draw here, you know uh, this is something. Okay, uh, this is something your, this is your rod that is used as a lever here, and I placed a fulcrum here. Okay, and this is your load, this is your effort. Okay, and I say that fulcrum is placed between your load and effort, so we call it a class 1, uh, you know class 1 levers. So what happens in a class 1 levers? Your effort arm and is effort arm also, mm, while having this that so so you have three classes of levers. Okay, so in class 1, you have fulcrum in between load and effort. Okay, and if we say that fulcrum is between load and effort, then you can place your fulcrum anywhere between load and effort, isn't it? So within class 1, okay, within class 1, we have different cases. If the fulcrum is placed near the effort point, or if it is placed near the load point, what will be the different cases? We will study it here. So let's say this is first case, where when the fulcrum is placed near the load arm. So when it is placed near the load arm, what will happen? So fulcrum is shifted towards load arm. Okay, that means your load arm will become smaller. Okay, and when your load arm will become smaller, what will happen to your mechanical advantage and velocity ratio? Just look at the equation. So by equation, we have already known this that your mechanical advantage you know, is the ratio of effort arm by load arm. So if your load arm is getting shorter, your mechanical advantage will increase. We have already seen this in in the previous question. Okay. So if you, the case one is you shift a fulcrum towards your load. So what will happen? Your effort arm will become greater than your load arm. And when your effort arm is getting bigger, your mechanical advantage will increase. And velocity ratio is also the ratio of same thing, effort arm by load arm. Okay. Or sorry, displacement of effort by displacement of load. So if you have a greater arm, that will make a greater displacement. That is, already you know it. Okay. The shorter arm will make a shorter displacement. Okay. So the example of this is very, common. You would have known pliers. So pliers are something that are used to cut a very thick metal, sheets or wires. So the electrical wires that you see, near your houses, so those are very thick wires. You can't cut it with simple scissors. You would need a pliers. So plier is what you have, a small load arm like this. Okay, and I think you can see it now better. And you have a longer effort arm. So those pliers are like this, that you have effort arm longer. So you hold it like this, okay, and you cut it like this. So uh, this give you a mechanical advantage greater than one. Okay, and let's take in another case where both these arms are equal. Your effort and load arm is equal. Then in that case, you are using it as a physical balance. You would have seen in various shopkeepers that they used to put, taraju. Taraju, you know already, right? So you put a weight on one of the, one of the section, and the other weight that you need to measure, you put it on another side, and it will tell you what is the exact weight. So if you have effort arm and load arm equal, that means the fulcrum is exactly placed between effort and load arm, then you will have mechanical advantages of 1. Now come to the case 3. So this was your case 2. Let's come to the case 3. For case 3, what if your fulcrum is placed near the effort arm, okay, effort point? So what will happen is that in that case, your effort arm will be less than your load arm. Okay. Okay. I forgot to tell you that in the situation where your effort arm is greater than your load arm, you you are what you are doing is you are applying a less force, and you are getting a greater force at the load point. Okay, because your effort arm is long, you are applying less force and you are getting more force on the load. Then you can say that you are using it as a force multiplier. Okay, and when there is a case that effort arm is shorter than load arm, you know, so Caesar is one example. So Caesar with uh, blades longer than handles. So let's say you have a Caesar like this. Okay, I'm making a very rough diagram, and this is your, you know, like this, something like this. So this is your fixed point. So this is your load arm now. Okay, and this is your effort arm. So as you can see that if you have effort arm less than your load arm, you are able to have a gain in speed. So gain in speed is basically that you are making a larger displacement on a load side by making a smaller displacement on an effort side. So you are making a less displacement and getting a larger displacement at the load side. That's why you call it as a that in this case the machine is using as a speed gainer. Okay. Now we will come to the second class of levers. So second class of lever is when your load is in between effort and fulcrum. Okay. And you know that when you are so what is the length of your load arm? This one. And what is the length of your load arm? This one. Because the load and efforts arm length is always measured from fulcrum point. Okay, so this is your fulcrum. So please tell me that in the class 2 type levers, if load is in between effort and fulcrum, which arm is greater? So I hope you are saying that effort arm is greater than load arm. You can also see it from picture, right? And this we have already studied. If your effort arm is, longer, then you can use it as a force multiplier. Means you are making a small effort and you are producing a high force on load, or you are making a large force to overcome that load. So such type of example is nutcracker. So you should know the difference between, case one. Case one is when you have fulcrum in between. In class two, you are having fulcrum, oh sorry, load in between fulcrum and effort. Okay, these are, totally different cases, but they are used as a force multiplier in both cases. So you have two cases how you can use it as a force multiplier. And so if I say that you need to work on lever as a force multiplier, you will say there are two way we can do it. One is when you have a fulcrum in between, but in that case you will make your effort arm longer by putting your fulcrum towards the load. And second is your class 2 levers, where you will have load in between, then evidently your effort arm will become longer. Okay, and then that is the way you can do work as a force multiplier. So let's come to the class 3 levers. So class 3 levers, nothing but the effort is in effort point is between fulcrum and load. So simply you know that it can be used as a speed gainer. Okay, and a speed gainer is what? That you are making a large displacement by making a small displacement in the F arm side. Simple case as we have seen in case of scissors. So now the question for today is how you can use levers as first force multipliers and second speed gainer. Please send your answers to me. Okay, I'll be waiting for it. And then for tomorrow onwards, we'll be looking into some numerical calculations. Okay, and if you have any problem in between, please get in touch with me. Thank you, everyone. I hope you like this. Okay, if you have any questions, you write it. Okay, send me a message. Thank you very much.